The universe is expanding. That much is famous. Galaxies are growing farther apart. Light is being stretched across space. And every second, the observable cosmos becomes a little larger. But that raises a question so obvious that it is surprisingly difficult to answer. If the universe is expanding, what is it expanding into? There must be something outside it, some greater darkness, an empty room waiting for the universe to fill it. Right? No. And the reason why may force you to abandon almost every picture of the universe you have ever seen. The first problem is the name, Big Bang. It sounds like an explosion. A tiny object detonating at one location and throwing matter outward into empty space. If that picture were correct, the universe would have a center. Somewhere, perhaps unimaginably far away, there would be the original point of the explosion. Galaxies near that point would move more slowly. Galaxies farther away would race outward, and beyond the expanding debris there would be untouched emptiness. But that is not what astronomers observe. When we look across the cosmos, distant galaxies appear to recede from us. The farther away a galaxy is, the faster the distance between us and that galaxy increases. At first, that seems to place Earth near the center of everything. But an observer in another galaxy would see almost the same pattern. From their location, distant galaxies would also appear to recede in every direction. Move to a third galaxy, and the pattern repeats again. Every galaxy can behave as though it is at the center, because none of them is the center. The galaxies are not simply flying through a pre-existing cosmic room. On the largest scales, the room itself is changing. Space is expanding. We know this because expansion leaves fingerprints in light. When light crosses the universe, its wavelength is stretched along with the space through which it travels. Light that began at shorter, bluer wavelengths arrives shifted toward longer, redder ones. Astronomers call this cosmological redshift. The effect grows with distance. Nearby galaxies show a mixture of local motions. But across truly cosmic scales, the pattern becomes unmistakable. The more space the light has crossed, the more expansion it records. We see another fingerprint in the cosmic microwave background. This faint radiation reaches us from every direction and comes from a time when the universe was only about 380,000 years old. It has been traveling ever since, while the universe expanded by an enormous factor. During that journey, its wavelengths stretched from the glow of a hot young cosmos into microwaves with a temperature only a few degrees above absolute zero. Expansion is therefore not merely a story invented to explain galaxies moving away. It is written into the light filling the entire sky. Imagine several dots drawn on a rubber sheet. If the sheet is stretched evenly, every dot moves farther from every other dot. No dot has to be the center of the expansion. From the viewpoint of any one dot, all the others are moving away, and the most distant dots separate fastest because there is more stretching sheet between them. That is close to what astronomers describe with the Hubble law. The greater the distance between two sufficiently remote galaxies, the faster that distance tends to grow with the expansion of the universe. But the rubber sheet creates another problem. A real sheet stretches into the room around it. It has an above, a below, and an outside. The universe does not require any of those things. The sheet is only an analogy for the changing distances inside space. The room around the sheet is not part of the model. We add that room because our brains are used to objects expanding inside larger spaces. Cosmic expansion is different. It is not necessarily an object getting larger inside something else. It is the geometry of the universe changing with time. Distances that were once smaller become larger. That sentence sounds simple, but it removes the need for an outside. Consider the surface of Earth. Ignore the planet beneath your feet and imagine that only the two-dimensional surface exists. You can travel north, south, east, or west, but there is no direction on the surface called away from the surface. Now begin walking in a straight line. You will never encounter an edge. There is no final fence, no cliff, and no sign saying that space ends here. Yet the surface has a finite area. It is finite, but unbounded. A two-dimensional creature living entirely on that surface could measure distances and angles. It might eventually discover that its world is curved. But it would not need to imagine the surface embedded inside our three-dimensional space. Its geometry could be described entirely from within. Our universe may work in a related way, except with 3 dimensions of space rather than 2. If space has the appropriate positive curvature, the universe could be finite without having an edge. A spacecraft traveling long enough in one direction might, in principle, return from the opposite direction, just as a traveler on Earth can circle the globe. There would still be no wall to cross and no exterior void waiting beyond it. However, we do not currently know that the entire universe has this shape. Measurements of the cosmic microwave background show that the observable universe is very close to geometrically flat. This background is the ancient light released when the young universe became transparent. In a flat universe, parallel lines remain parallel, and the angles of a sufficiently large triangle add up to approximately 180 degrees. That may mean the universe is infinite. But flat does not automatically prove infinite. A space can have unusual connections, known as its topology, that allow it to be finite even while its local geometry remains flat. A classic example is a three-dimensional version of a looping video game world. Leave through one side and, eventually, return through another. Cosmologists have searched for repeating patterns that might reveal such a structure. So far, there is no convincing evidence that we live in one. The honest answer is that the entire universe may be infinite, or it may be finite on a scale larger than we can detect. Either possibility can exist without an ordinary edge, and this is where the question becomes even stranger. How can something infinite expand? If the universe was already infinite a billion years ago, how can it be larger today? Surely infinity cannot gain more space. But expansion does not require infinity to acquire an edge and push it outward. It means the distance between locations changes. Imagine an infinite line marked with numbers. Every number has a neighbor, 1 unit away. Now double every distance. The line was infinite before and it remains infinite afterward, but the separation between its points has increased. It did not expand into anything. Its internal scale changed. An infinite universe could therefore have been infinite at the earliest moments we can describe and still be expanding today. Matter and radiation would once have been far denser and hotter, not because all of infinity was compressed into a tiny ball sitting somewhere, but because every region of the universe was more compressed than it is now. The Big Bang was not an explosion at one location. It happened everywhere. Every galaxy we see developed from a region that was once part of that hotter, denser universe. There is no direction in the sky that points back toward the Big Bang, because looking far enough in any direction means looking back toward the same early cosmic history. So when illustrations show the Big Bang as a brilliant point expanding into darkness, they are not maps. They are timelines disguised as pictures. The center of the illustration represents an earlier time, not a location you could visit. But perhaps the universe has no physical edge while the part we can see does. That is true. The observable universe has a horizon. Light travels at a finite speed, and the universe has a finite age of about 13.8 billion years. We can only receive information from regions whose light has had enough time to reach us. Because space expanded while that light was traveling, the most distant regions we can observe today are now much farther away than 13.8 billion light-years. The present radius of the observable universe is roughly 46 billion light-years. This horizon is real, but it is not a wall. It is a boundary in information. Beyond it, there are almost certainly regions whose light has not reached us. We cannot currently see them, no matter how powerful our telescope becomes, because the limitation is not the brightness of the object. The limitation is whether its information has had enough time to arrive. If you could instantly travel billions of light years away, you would not find the edge of everything. You would have a different observable universe centered on your new location. You could see some regions forever hidden from Earth, while losing access to others that Earth can see. Everyone carries an observational horizon around them. That is why the visible universe can have a boundary even when the universe itself does not. If space is expanding, should you be expanding too? Should atoms grow? Should Earth drift away from the sun? Should the distance between your eyes increase with the universe? Fortunately, no. Cosmic expansion dominates across the enormous spaces between distant, unbound groups of galaxies. Inside systems held together by gravity, electromagnetism, or other forces, those local forces overwhelm the tiny effect of expansion. Atoms do not expand because electromagnetic forces bind them. The solar system does not expand because gravity controls the planet's orbits. Even our local group of galaxies remains gravitationally bound. The Milky Way and Andromeda are approaching one another despite the expansion of the wider universe. Space is not a substance that drags absolutely everything apart at the same rate. Expansion describes how the large-scale geometry evolves when local binding forces are not strong enough to resist it. Some galaxies recede from us faster than light. This does not mean they are breaking Einstein's speed limit by racing through their local space. Special relativity prevents objects from locally passing one another faster than light, but it does not impose the same limit on how quickly a sufficiently large amount of space can grow between extremely distant locations. The galaxies are not firing engines beyond light speed. The distance separating us is increasing because the intervening universe is expanding. For some regions, that expansion means light emitted today will never reach us. The space between us and them grows too quickly for the light to make progress across the full distance. They do not cross a physical wall, they cross a horizon in our future. The universe becomes larger, while the portion we can ever communicate with may become lonelier, and the expansion is accelerating. Observations of distant supernovae, the cosmic microwave background, and the distribution of galaxies indicate that something we call dark energy has become the dominant influence on the universe's large-scale expansion. We know what dark energy appears to do. We do not yet know what it is. It may be energy inherent to empty space. It may be a field that changes over time. Or our description of gravity may be incomplete at the largest scales. Whatever the explanation, the acceleration does not mean the universe is pushing harder against an exterior boundary. It means the scale of distances inside the universe is evolving at an increasing rate. So, what is the universe expanding into? The most accurate answer is that the question assumes something science does not require. The universe is not expanding into a larger container, at least not in any model supported by evidence. There is no measured cosmic wall, no known exterior, and no privileged center from which everything is fleeing. The universe expands by changing the distances within itself. If it is infinite, it remains infinite while its internal scale grows. If it is finite and unbounded, it can grow without developing an edge. And if some higher dimensional reality exists outside our universe, current observations have not shown that cosmic expansion needs it. This is difficult to picture because every object in human experience has an outside. A balloon expands into air. A fire spreads into unburned forest. An explosion throws material into surrounding space. But the universe is not simply another object inside the world. It is the system that gives inside, outside, distance, and direction their physical meaning. Asking what lies outside all space may be like asking what lies north of the North Pole. The words remain familiar, but the direction has disappeared. And perhaps that is the most unsettling part. The universe does not have to fit inside anything. It does not need a room, a border, or a darkness beyond the final galaxy. There may be no final galaxy. There may be no edge to reach. Only more space, carrying every distant world away from every other, while the light between them stretches, reddens, and slowly fades. The universe is not moving into the unknown. The universe is changing what distance itself means.